Good morning, guys, and welcome back again to Algebra 1 today. It is Friday, September the 5th, and I'm away at a meeting for planning for Algebra 1 with our curriculum resources that we're using. So I'll be gone for the day. You guys have a sub today as you guys are working through your eighth lesson of our first unit in the material. Today, we are going to be working primarily with arithmetic sequences. And we're going to start developing some strategies that we can utilize to find some missing terms in a sequence using what we've seen so far about this particular type of sequence. As we go, you've probably noticed that we have some updates to our seating chart here. Instead of tables, we are now arranged in rows for the time being. So please make sure that as you're filtering in and you're putting your phones away in the wooden caddy with the phone slot assignments, that you're also finding your correct assigned seat. I'm going to make sure that the sub has an updated seating chart. So you guys should be at the correct seats shown here on the diagram. Top of the diagram is going to be closer to the front of the room. Bottom of the diagram there is going to be closer to the back. The right-hand side is going to be closer to this interior wall towards the teacher's desk. And the left-hand side over there is going to be closer to the windows. This will be our seating chart for a few weeks. As we go, we'll sort of determine whether we can go back to our table groups or if this is going to be maybe a little bit better for our structure of our class. But it's to be determined. What I want to do as we get rolling into our time for the day is quickly work through a warm-up for the retrieval problems here on page 67. We're continuing to practice this idea of writing equations when we're looking at sequences, either arithmetic, geometric, or sometimes neither. So take a moment with your group mates. I want you to look through each of these sequences on page 67, and I want you to decide, do you think they're arithmetic, geometric, or neither? If the sequence is arithmetic or geometric, I want you to attempt to write the equation, either recursive or explicit. That's going to match this scenario. All right. So in this particular exploration, we're on page 67. In particular, what we're trying to do is determine what kind of sequence we're working with. I might start with, say, this guy on the left-hand side, where if I go from 112 to 56, and then if I go from 56 to 28, I know for sure that this is some kind of decreasing sequence. What I'm not quite sure yet is whether this sequence is arithmetic, geometric, or neither. If I take a look at 112 going to 56, I could have gotten there by subtracting 56, but if that was going to be an arithmetic sequence, I'd be able to take 56 away from 56 and get the next term in the sequence to be 0, which is not necessarily what we see here. We see that the value is actually 28. So if I think about it maybe a little bit differently, and I say, okay, to go from 112 to 56, it's kind of like I cut it in half. And then to go from 56 to 28, I cut it in half again. What we're going to see here is that this is evidence of a geometric sequence. Now, when we write a geometric sequence, we often talk about a common ratio, which I'm going to start to refer to as this term R. This common ratio is usually something that we're multiplying by over and over again. So you may have recognized in this pattern that we're dividing by 2, but how I'm going to write that is I'm taking half of a term to get the next one. So as I write a recursive definition, I might say here that f of n equals half of f of n minus 1, which is my previous term. But I also got to specify where I start the sequence. So in this case, I might say f of 1, the result of the first term of the sequence, is 112. And then that would work for a recursive definition. If I wanted to write an explicit definition, I know the common ratio, and I know I have this first term of 112, but where we got to be careful is if I make use of these terms as I see them. So if I say the first term is 112, the common ratio is a half, and then I'm just going to the nth power. Plugging in n equals 1 for that first term of the sequence is ultimately going to get me an output of 56, which is the second term of the sequence. So if I'm not careful, and if I don't do that n minus 1 power to sort of shift it back to being the right output for that term of the sequence, I'm not quite going to have the correct explicit equation. A different way that I could write the answer for this, though, is to think about going back to the 0th term of the sequence. So I know going forward in the pattern, I'm dividing by 2, but if I were to go backwards and multiply by 2 instead, a different way that I could envision this is to say that I could have 224 as like my 0th term. I'm still multiplying by half as I go, but then I don't have to worry about decrementing the sequence. I can use n directly instead of n minus 1 in that case. If I test it out with, say, n equals 0, I'll see 224 times a half to the 0 is 224. If I try n equals 1, then 224 times a half to the first is 112, and I've got the correct pattern of behavior there. Now, for this guy kind of in the middle, if I go from 5 to 10, or 10 to 17, or 17 to 26, I might initially think that to go from 5 to 10, I'm multiplying by 2, which would work. But it's not going to be the same from going from 10 to 17. If I try and double 10, I get 20, not 17. So we have evidence that this is not a geometric sequence, but it could be arithmetic. The problem here is if I want to go from 5 to 10 under addition, I've got to add 5. But then to go from 10 to 17, I've got to add 7. And then to go to 17 to 26, I've got to add 9. And because that's not a consistent pattern that I'm adding by, I know it's not an arithmetic sequence either in this case. So given that it's neither arithmetic nor geometric, we're not going to be able to write a rule for something like this yet. But it is something that we'll start to revisit as we go a little further in the curriculum. For this last guy on the right-hand side, if I go from -30 to -13, and then -13 to 4, I know here that my sequence is increasing. And one thing that I might initially check is to say, okay, is it arithmetic? If I go from -13, or rather -30 rather, to -13, and I'm adding something, I might be adding here by 17. But I want to check and make sure that that's consistent. So as I go from -13 to 4, I see that that's also plus 17. So I know for sure in that case that I've definitely got an increasing arithmetic sequence on my hands. So if I wanted to write my recursive equation, I could say that the next term, f of n, is equal to the previous term, f of n minus 1, but I'm just going to add 17 to it. And it's how I step through the process. I also want to specify where we start the sequence. So here, if I have like a first term, which is -30, I might write that as f of 1 equals -30. For an explicit equation, if I want to capture that repeated addition a whole bunch of times in a row, what I'm going to write here is this common difference, 17, and then I'm going to multiply it by n. If I write 17 times n, what I'm saying there is I'm going to do plus 17, plus 17, plus 17 n times in a row. I've also got to say where the sequence starts, which in this case is this -30 terms, that constant. The only problem with this, kind of like we saw in that first scenario, is that if I check it by plugging in n equals 1, I get 17 minus 30, which is -13, and that's not the first term of the sequence, it's the second. So if I want to use this 17 and the -30, I'm going to have to be careful here and say that it's 17 times n minus 1. I've got to shift it back a step in order to capture the correct values of the sequence in order. A different way that I could write it is to use f of n equals 17n, but then I'm just going to have to go backwards to what we would refer to as like the 0th term of the sequence. So if going forwards, I add by 17, going backwards, I subtract by 17. So I could write 17n minus 47. Either one of those equations works if I check it against the data that I have here. If I plug in n equals 1, I get -30 out of both of these guys. If I plug in n equals 2, I get -13 out of these guys. So either way are potentially good solutions to go. From there, I think maybe what we'll do is take a look at this jumpstart, where we're going to take a look at some missing terms of a sequence, and then we'll start launching into our lesson for today. So if I give you these 3 sequences, what I want you to do real quick with your group mates is try and figure out the missing values. I want you to try and identify what kind of sequence we're working with. either the common ratio or the common difference. And then I want you to go ahead and try and make a prediction as you go from there. So as we take a look at these sequences, and I go from, say, 7 to 11 or from 11 to 15, it appears to me that we're adding by 4 here in both of those cases. 7 plus 4 gets me 11. 11 plus 4 gets me 15. That would strike me as an arithmetic sequence where that common difference, this value d, is plus 4. So if I wanted to find some of my next terms, I could do 15 plus 4, which is 19. I could do 19 plus 4, which is 23. I do 23 plus 4, which was 27. And that would be maybe a way to go for that particular problem. If I look at negative 32 going to negative 39 and then negative 39 to negative 46, what I'm going to notice here is I could think of like adding negative 7, or I could think about just losing 7 directly. So this is also an arithmetic sequence. But what I'm going to see here is that my common difference is a negative number. That's the thing that I'm adding over and over and over again. So if I go from negative 46 to the next term, it's going to be whatever negative 46 minus 7 is. And that's going to give me, I think, negative 53. Negative 53 minus 7 is like negative 60. Negative 60 minus 7 is like negative 67. And then I got those guys figured out. For this last one, when I go from negative 6 to 6, I could be adding by something, but I could also have multiplied it by negative 1. So some students will see that and they go, well, maybe that's geometric if you're multiplying by negative 1 to switch the sign. But if it's geometric, then that would mean the next term in the sequence after 6 should go back to being negative 6. And it's just going to alternate back and forth, right? So here, it's not quite a geometric sequence. It's arithmetic. To go from negative 6 to 6, I add 12. And then if I check that with the next term to make sure it's consistent, I add 12 to 6 to get 18. So all of these ultimately turn out to be arithmetic. So as we identify this common difference, that's going to allow us to figure out our next terms, where 18 plus 12 is going to get me 30. 30 plus 12 is going to get me 42. 42 plus 12 is going to get me up to 54. And then we've got our missing terms. So the jump start in that is mainly designed just to kind of get the gears turning for the types of sequences that we're going to be working with primarily in our lesson for today. As we wrap things up with Unit 1, we're on the final few topics for the material, and we're going to start getting ready to do our second part of our summative assessment for the unit, which is going to come up a little later, about halfway through the month on the 15th or the 16th. We'll take one last CFA assessment to get some feedback and get you guys across the board with some of the last bits of the material that you might see on our summative assessment. From there, we are pretty much done. And we're going to start moving into the transition from talking about sequences to functions when we start getting into the material for Unit 2. Bear in mind that the final deadline for any of the Unit 1 Ready, Set, Go submissions are going to be on September the 16th. So as we get closer to that date, you want to make sure that you're keeping up with your Ready, Set, Go submissions for everything from 1.1 up to 1.7. Otherwise, what we're going to be working with is our understanding of how to identify sequences using representations, but we're going to, in particular, focus on the skill of how to predict missing terms. We're going to be introduced to a kind of an interesting scenario where we're going to know some first terms and then the last term, and we're going to have to sort of figure out a strategy to find things in the middle. We know arithmetic sequences have this common difference where it's this repetitive adding by a constant. Sometimes the sequences increase, sometimes they decrease. What we saw in, I think, lesson 1.6 is this sort of table, this framework for understanding the notation that we use to represent the explicit or the recursive functions that we can write these cases. You'll notice that in this table, we often refer to the common difference as this plus d term. And the initial value of the sequence, we usually refer to as this plus c term. So depending on how you think about it, you may think about this less in terms of like values that are being like plugged in this sort of template approach, but this is just sort of a different way to look at it. So when I say like n or n minus 1, we mean like the current term of the sequence. When we say f of n or we say f of n minus 1, what we mean there is something like the output of the sequence, the actual value of the sequence. So C is our first term. F of n is like the next term. F of n minus 1 is the previous term. So we've been playing with this vocabulary a little bit, but I wanted to make sure that we kind of continue to reinforce this more symbolic way that we're categorizing our results. Similarly, we've been talking about sequences that could be geometric. Now, today we're primarily focusing on arithmetic sequences, but when we meet again for lesson 1.9, we'll talk a little bit more about this particular context when it's geometric. So I'm going to move on to our launch activity for today. And here on this slide in the notes, which is on, I believe, page 65 for you guys, you're going to see some tables where every single one of them is some sort of arithmetic sequence. What you're going to notice is that there's a lot of missing terms in these tables. So that topmost table has the first and the last term, but it's missing the middle one. The one below that is missing the first three terms in the middle. And then this guy at the very bottom here, I've got to add in that seventh term real quick. It looks like I got a typo. But in your notes, you should see that they all have the first and the last terms. What I want you to do real quick with your group mates for maybe like 3-4 minutes is try and figure out a strategy for how you can find those missing terms that are caught in the middle. You may see here that you have the same idea or maybe some different ideas than the person next to you, but I want you to try and come up with a strategy for how to find these guys. So for these three sequences, we know that there are some missing terms, and we're trying to come up with some strategies that are going to help us try and figure out what is missing and how we can use that as we go a little bit further when, as we go, the length of the sequences is increasing. So this first one that we have here kind of in the middle, we know that it's going to start with a term of 5 and it's going to end with a term of 11. So another way to say that is like the first term's 5 and the third term's 11. It's this middle term here that I'm missing, that second term in the middle of the sequence. Now, if I'm thinking about how to figure out that missing value, one way that I could approach this problem is to say, okay, if it's arithmetic, I know for sure that I should be adding by some kind of constant. So I'm going to do 5 plus something to get that number in the middle, but then I'm going to have to do that number plus something to make sure I end at 11. So I've got to go forward a certain number of units from 5 and maybe backwards a certain number of units from 11, and I've got to make sure that I'm doing the same distance away. So one way to think about it is if I picture it on a number line, I could go from 5 to 6 to 7 to 8 to 9 to 10 and then to 11. And if I want to figure out the thing that's like equidistant away from 5 and from 11, the thing that's kind of like caught in the middle there, what I'm going to notice is if I sort of diagram it out with a number line, that value must have been 8. So the common difference for this sequence must be plus 3, because if I do 5 plus 3, I get 8, and if I do 8 plus 3, I end at the correct value, which is 11. So knowing that this is an arithmetic sequence, I could kind of think about how to get to that end point there, and then that would give me a final answer. A different way that I could try and tackle this that some of you guys may have thought of is you may have thought, well, I need to find the number that's halfway between 11 and 8. Halfway between 11 and 5, rather. So some of you guys may have run a calculation where you say, hey, if I do like 11 minus 5 divided by 2, which is the same thing as getting something like 6 divided by 2, which is 3, that is a way to find the common difference. You figured out how far in to go from the outside edges to get that 8th value there, that second term of the sequence, which should have a value of 8. If you're thinking about this kind of strategy, where you're thinking about like the halfway point, using a strategy that involves something called the arithmetic mean between two numbers. You're essentially averaging out those two numbers to find what's caught in the middle. And that's a good way to approach it. If you take a look at this bottommost problem, or maybe the one in the middle, I should say, we now have 5 terms in the sequence where the first term is 18 and the fifth term is negative 10. I recognize here that my sequence is going to be decreasing. So I go from like 18 to something. I go from something to something else. I go from that something else to a third thing. And then finally, I go from that to negative 10. What's going to be kind of interesting here is if I'm trying to like think strategically about how to find that missing value, if I'm trying to figure out like a way to do that, I could maybe go back to this idea where I'm thinking about a number line. What's going to be interesting here is that my sequence is decreasing. So if I'm drawing this on a number line, I've got to put 18 further to the right and negative 10 further to the left. Now, I've got a lot of numbers that are going to be caught in between there. I'm going to have like negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0. And I'm going to have everything from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, all the way to 18. So it's kind of harder to picture here. And if I'm thinking about like a halfway point between, say, 18 and negative 10, well, one thing that I could do there is say, okay, this distance, when I do 18 minus negative 10, is 28 numbers. So the halfway point between those values is going to be 14 in from either side. And that might tell me what the third term of the sequence is, in the sense that if I do, say, negative 10 plus 14, I get 4, or if I do 18 minus 14, I get 4, that would work. And then I can sort of use that approach to say, okay, what's halfway between, say, negative 10 and 4? Where if I see that distance there is, say, 14 units, then the halfway point is 7 units in. And same thing over here on the other side. If I want the halfway point between 18 and 4, I've got to go 7 units in to try and capture that. That's one way to potentially find our answer. So if I do 18 minus 7, I get 11. If I do negative 10 plus 7 to go backwards here, I get like negative 3. And then I want to double check it, right? 18 minus 7 gets me 11. 11 minus 7 gets me 4. 4 minus 7 gets me negative 3. And then negative 3 minus 7 gets me negative 10. That seems to work nicely, right? So that must mean for this particular sequence, my common difference was something like negative 7. I was subtracting 7 every single time. Now, that's a strategy where we're sort of using that arithmetic mean to figure it out. That doesn't necessarily mean that that may have been the only way that we could have done it. Another thing that may have occurred to you guys is that if you count like the number of blue arrows here, I'm making 4 jumps to go from the first term of the sequence to the fifth term. And I know my total distance that I'm going in terms of the value, 18 down to negative 10. I know that that distance on the number line is something like 28 units. So one thing that students may have done here is you guys may have been looking at this and say, okay, if I've got to go 28 numbers, but I've got to do it in 4 groups, 4 jumps, I could do 28 divided by 4, which gets me 7. And if I know the sequence is decreasing, then instead of adding 7, I go down by 7. So I do 18 minus 7, 11 minus 7, and that'll get us where we want to go as well. So there's not just one way to kind of find the answer here. If you take a look at this bottommost table, this is where it gets kind of tricky. If I try and shift gears and I say here, okay, I've got to go from the first term to the 7th term. So that's like 6 jumps down the line. I could find a halfway point, but the hard part there is when I have an even number of jumps like this, that halfway point is going to get kind of interesting to calculate. I know that the halfway point between 12 and -6 on the number line is going to be whatever's literally halfway between these values. So if that distance is like 18 units and I cut that in half, I've got to go 9 units in from either side. So that's going to be like 3 that I'd have to write. But notice if I want to find the halfway point between, say, 12 and 3 or 3 and -6, it's not going to be a value inside the table. It's going to be one of these like boundaries. So approaching it by thinking about averages in that case might be a little more difficult in this particular setup. So it was a useful strategy early to kind of help us develop maybe an alternate strategy, but a different way that I could tackle this is to think about the number of jumps that I've moved. I know that I'm going to go 6 jumps into the future, and I know the distance that I need to cover between 12 and -6 is 18 units. So I've got to go 18 units down eventually. I've got to do it in 6 jumps or 6 groups. So I think a lot of you guys may have recognized here that you could go 18 divided by 6 gets me a value of 3. So if my sequence is decreasing, I have to subtract 3 over and over and over again. So go 12 to 9, 9 to 6, 6 to 3. That's matching what we saw with that average approach. 3 minus 3 would get me 0 on the 5th term, -3 on the 6th term, and then finally we end at -6, which is where we want to be. So there's not just one way to look at this guy. There's a few different ways that we could potentially tackle this. And as you were working through that, hopefully you guys were starting to see that and really try and put those strategies together in this context. So again, not just one way to answer the problem. Let's try maybe this guy or say this guy really quickly with the Explore page on 66. I want you to try maybe taking 3-4 minutes and try and find the missing terms in each of these scenarios. And then we'll bring it back together in the video and get ready to close up our notes for today. All right. So using any of those methods that we developed previously, our goal here is to find the missing terms in the sequence. When I start with the first term is 50 and the 4th term is 86. If I'm thinking in terms of like the number of jumps here, I'm going to notice that I make 3 jumps, but I have 2 spaces in the box. So if I was trying to like average things out and find out what's in the middle, I wouldn't necessarily end up in the table. I would get something caught between those values at like the 2.5th term of the sequence, which is not exactly easy to think about here. So this might be a place where that arithmetic approach where we're like averaging things out doesn't work as effectively. But if I think about this, say, in terms of jumps, where I say I've got to go 3 jumps and I got to cover a distance in this case of whatever 86 minus 50 is. So I've got to cover 36 units in 3 jumps. Well, that would tell me that my common difference here is 36 broken into 3 groups. So that's plus 12. So once I know that common difference, what I can do is use it in the table to sort of increment step by step in sort of a recursive process. So 50 plus 12 would get me something like 62. 62 plus 12 would get me something like 74. And then 74 plus 12 would get me something like 86. So that's potentially one way that I could work my calculation here. If I look at that distance as the value of the last term minus the first term, and then I divide by the number of jumps that I'm getting, that could potentially work quite nicely. A different way that I could think about this, if I was setting up maybe more of like an algebraic equation, would be to say, hey, 50 plus some common difference, and then 1, 2, 3 jumps in the future is going to need to equal this output of 86. Now, if I'm thinking about this more algebraically, where I say 50 plus 3 jumps of some unknown length equals 86, I'm trying to solve for this variable d. And if I was trying to solve for that variable and get it by itself, what we'd see here is that I've got to subtract 50 from both sides. So that I've got like 3 times d equals 36. But then how do I undo multiplication by 3? Here I can divide by 3. And that's going to give me the same answer, just a different way. I'll see here that my common difference is 12. So you could think about it kind of more like grouping in hops and then thinking about how far in each hop you have to go. And then that sort of leads into like maybe this more algebraic equation approach where we say 50 plus 3 unknown long hops equals 86, gets us that same common difference. Let's try maybe this other one where we go on to the next page. Here, if I start at a value of 40, but then my sixth term has a value of 10, I know that this guy's decreasing. So I'm probably going to end up with a common difference in this case that's a negative number. Now, if I'm thinking about maybe that first approach that we tried, I know I'm going 40 to something, something to something else, something to something else, something to something else, and then finally something to 10. That's something like 5 jumps. And the distance that I have to cover on the number line there is 40 minus 10. That's going to be something like 30 units that I have to go in 5 jumps. So if I think about my common difference as 30 units broken into 5 groups, I'll see here that in each jump needs to be 6 units long. But if I'm decreasing in this case, if I want to be going down in value instead of up in value, I need to get my common difference to be something like -6. So if I'm thinking about how to do that, another way that I could have found this distance would be to do 10 minus 40, which would get me -30. And then -30 divided by 5 could get me something like -6. So if I think about this like last term of the sequence and its value, and I think of it losing the first term of the sequence's value in this distance and sort of rearrange this, that allows me to get that negative that way. So 40 minus 6, that gets me like 34. 34 minus 6 gets me 28. 28 minus 6 gets me 22. 22 minus 6 gets me 16. And then 16 minus 6 gets me 10. So that worked. A different way, if I'm thinking maybe more algebraically, is to say that 40 plus 6 of these unknown jumps needs to end up equaling the value 10. If I'm thinking about this algebraically and I subtract the 40 from both sides, notice that's where I get a negative number. And then that's going to allow me to get that common difference to not be increasing, but decreasing. So I'd see 6d equals -30. When I divide both sides by 6, there is my common difference. There I'll get something that's going to look like -6 in this case. Is it 6 jumps? No, it should be 5 jumps. My bad. Get the eraser out. There we go. So if I'm doing this in 5 jumps, there we go. That's going to get us that common difference that we're looking for there. And it's going to be negative. So we captured the right kind of behavior there. For a decreasing sequence, we usually refer to that common difference as being a subtraction or -6. But either way, we developed a strategy in that case. So that's kind of the method. There's maybe one more here in the Explorer page that I think we'll do as a warm-up when I come back, just to sort of check on the process. What I want to bring together there is this sort of larger recognition of what strategies worked sometimes and what strategies worked every time. When the sequences are small and there's not many terms, thinking in terms of like the averages will work so long as there's like an odd number of spaces that we have to fill. If I'm thinking about that table and I have like an even number of spaces, that's where that average didn't quite cut it. So in some instances, thinking in terms of that average distance between two things might work. especially if you can break it down so that there's like an odd number of gaps in the table, and then in each half that you created, there's another odd number of gaps. But it doesn't work as well when there's even numbers of gaps. On the other hand, if I was thinking in terms of like the number of jumps that I've gone in the table, that allowed me to work regardless of whether I had even or odd numbers of gaps within the table. So one thing that we'll want to do as we sort of finalize the results in this lesson is kind of take that strategy that definitely works and put it together to think more about how to formalize that. I think we'll maybe skip that last one there and make that a warm-up as well. What I don't want is this video to be too long. So we're going to hit our key takeaways here, and then you guys should have some nice work time to start working through the practice assignments for some of our Ready, Set, Go submissions. The big idea here at the end of our section for the notes is that if we know the first and the last terms of an arithmetic sequence, there's maybe a couple of ways that we can think about how to find the things that should be there in the middle. One way is to think about finding that common difference by taking the distance that we're covering on the number line and dividing it by the number of jumps that we have to cover it. So if I'm looking at like the right-hand side of the board here, you can think of the last minus first there as being like the distance we're trying to go. And the number of jumps is like the number of hops in the table that we had to go from first to last. You'll notice here in this more like symbolic representation, f of n is going to be that last term, where f of 1 is going to be the first term. You'll also notice that we said the number of jumps is equal to n minus 1. What you may have noticed is that if I have like a first and a sixth term, I always had 5 jumps to go to get to the end. And if I had like a first and a fourth term, I had 3 jumps to go to get that last term. So it'll always be the number of terms total in the sequence minus 1. If you're thinking more algebraically, on the left-hand side of the board, another way to find our answer is to say, okay, the first term plus the common difference times the number of jumps should eventually equal the last term. And that's where I'm sort of making use of this notation again, right? The common difference is D. The number of jumps in this case is always the number of terms minus 1. F of 1 is the first term, and F of n is the last term. Both of these strategies let us figure out that common difference. And once we know the common difference, we kind of take a recursive approach where we use it step by step to find the missing values. Once we know the common difference, we could create an explicit equation instead of a recursive one. And that might be useful if you want to go farther in the future with like a prediction. And that's where we'll kind of come back to this problem in the Ready for More. You're welcome to try this if you'd like, especially as we get ready to switch gears into our work time and start working through the practice. But again, if I wanted to go in the future, I would need an explicit equation, and that'll be something we kind of cover as our next warm-up. So if you're curious, you're welcome to give that a go, but we'll take some time to discuss it later. For the rest of the time in class today, as we get ready to go into the weekend, I want you guys to start working through your Ready, Set, Go practice for today's lesson 1.8. I also want you guys to notice that we've got Ready, Set, Go practices for 1.7, 1.6, and 1.5 as well. So as we get closer to the end of the unit, you want to make sure that you're starting to finalize your Ready, Set, Goes and submitting them for credit. If you go on our Schoology page, what I'm going to try and point out here is that the Ready, Set, Go for 1.5 is going to be a file upload submission. So instead of doing our usual, where you're sort of entering in the values in that sort of like quiz format, for this one in particular, I want you to take a photo using like the laptop camera for your Chromebook or like a scanner outside of class. And I want you to upload a picture, a link, or a scanned submission for that lesson for 1.5. The main reason for that is just because there's lots of graphing by hand, and that's kind of hard to capture in that quiz format. So for 1.5 in particular, you may notice that that one's a little bit different, but otherwise it should work just fine. Apart from that, though, I will see you guys again after the weekend. I would definitely prefer to be in class with you guys than at this meeting, but it's required for us Algebra 1 teachers to go to these just to make sure that we know the curriculum and that we're delivering it accurately, that we're making the best use of our resources. So in the meantime, I hope you guys enjoy your weekend. I will see you guys after